In this module, we're going to review the basics of superposition. First, we're going to review the concept of linearity, which was covered in a previous module. System R is linear if for two inputs I sub 1 and I sub 2, with outputs k sub 1 and k sub 2, the response to the weighted sum of inputs, in this case A1 times I1 plus A2 times I2, is equal to the weighted sum of outputs, in this case A1 K1 plus A2 times K2. So a system that satisfies this relation is known as a linear system. The other concept we want to review is that of the impulse response. That is simply the response of the system to a delta function input, in this case a Dirac delta function, and the impulse response here is denoted h of x. So for example, for an X-ray system, we could have a point object, and the impulse response would be the X-ray image of that point object. Here's some notation for an impulse response. In here, we're saying that the impulse response is looking at the response of the system to a Dirac delta here located at xi, and it has an impulse response that also has a xi in it, suggesting that the impulse response can differ depending on the location of the Dirac delta function. So for example, we might have a Dirac delta located at 0, and it might have some impulse response we call h of x, comma 0, or semicolon 0. And let's say we have, in general, a delta function located xi, some other location xi, and that might have a completely different impulse response, h semicolon xi. And so in general, we're allowing the impulse response to vary as a function of the input location of the delta function. So we're keeping things fairly general at this point. For a 2D system, the impulse response is located at xi eta, and for each of those possible locations of the delta function, we could have a different impulse response. So now let's move on to superposition. And what superposition is going to do is we're going to apply linearity and find that using linearity, we can show that the response of a linear system to any input is going to be a weighted sum of impulse responses. So let's look at a specific example here. Here we have g sub m, and in this case there's just three terms, weighted sum of Kronecker delta functions in this case. So let's be more specific and actually draw out a specific case. So let's say it's 1, 2, 1. At the 1, 2, and 0, these are the locations. And so in this case, g sub 0 equals 1, g sub 1 equals 2, and g sub 2 equals 1. So those are the weights for the shifted Kronecker delta functions. And we now can consider looking at some impulse responses. So for example, the Kronecker delta at 0 could have some impulse response. In this case, let's say the impulse response looks like this: 1, 2, location 0 and 1. And so this would be h of m prime, 0. And in this case, we're using m prime to denote the output coordinates, and those could be identical to the input coordinates m, for example, if those are both indexing time, but in general, they can be also different. So now let's look at if we have delta m minus 1, and let's say in this case, there's a slightly different impulse response. So these are 1, 1, and this would correspond to h of m prime, 1. And we could also look at delta of m minus 2, giving rise to another impulse response. Let's say it has 1 and 1/2. And this would be indexed to have an impulse response denoted as such. So these are the impulse response. Those are the impulse responses to the different Dirac delta functions. And so now what we say is, because the system is linear, we can simply multiply each of these responses by their weights. So in this case, we multiply this by 1, which is the value of g sub 0. We multiply this by 2. We multiply this by 1. And then we sum up all those responses to get our final output. Okay, so here we're applying the scaling property, and here we're applying the additive property of a linear system. So let's look and see what that might look like. So the first impulse response is just scaled by 1, so it just looks like this. The second impulse response is scaled by 2, and we add on, so 2 and 2. And then the last impulse response is scaled by 1, so we add on 1, and then a half. These happen at 0, 1, 2, and 3. So when we sum up everything, it looks something like this. There'll be a 1, 4, 3, because that was a 1 up there, and then 0.5 here, location 0, 1, 2, and 3. And so our final output is simply a weighted sum of the individual impulse responses. Here we're seeing things in a little more abstract form, where we have the two lines we've seen before, where we have our input and our impulse responses. And now we just want to go step by step and look at what would be the response of my system to that input. So we just can write it out. We replace it, the g sub m, with its signal expansion. And now here we distribute the linear system or the linear operator over the different elements in the sum, and that's using the additive property. So that allows us to take the L and apply it to each of the terms, and then we just add it up, because for a linear system, the response to a summation is just the sum of the responses. And then from the scaling property, we can factor out these scaling terms, okay? Because for a linear system, the response to a scaled version is just a scaled version of the response. And so that's there. And now we simply replace each of these terms with their impulse response. And now we have here a weighted sum of impulse responses. And we can write this in this notation with a summation sign. If we're dealing with a continuous time function, then instead of a summation for our signal expansion, we have here this double integral. And in this case, this is because we're dealing with, it's both continuous and also a 2D function. And so we have these 2D Dirac delta functions and also these weighting terms. And now let's see how we get the response. So the response of L given some input, first we do the signal expansion here. And then we apply linearity, and we're able to move that linear operator within the integral signs because of the additive property. Essentially, we can take that linear operator within inside the addition, and that's just because the response to the summation is the summation of the responses. And furthermore, we can take this weight and keep it outside here because the response to a scaled version is simply a scaled version of the response, and that's the scaling property. Whoops, sorry about that. And finally, we can write this as each of these terms here. L, the linear system response to these Dirac delta functions is simply these impulse responses. So we have these weighted sum of impulse responses where the summation now is using continuous integrals.